Okay, good morning, everyone. Welcome to this session. How are you all doing? Nice. I should apologize in advance if I'm making you guys really exceptionally hungry just before the lunch. But I'll make sure we'll enjoy this session together. So, quick intro. Who am I? I am Swetha Golla. I work as expert application architect at Discover Financial Services. And I've started my career as Java engineer 18 years ago, and played different roles in the technical ladder and transformed into architecture. So I've been playing a role of architect from more than 7 years now, and I also have my expertise in cloud migration. I was fortunate to lead some good, complex applications from on-premises to cloud using various strategies like, rehosting, replatforming, and even re-architecting. So it was fun, and I'm here today to share all those learnings and experiences with you. All right, before we get into the agenda, very quick question to make us understand why we are here today. How many of you have received a call in the midnight that system is crashed and it needs to be fixed? We have all been there, isn't it? Yes, and that's exactly why we are here today, to discuss about architecture and significance of architecture elities, and how do they help us in building reliable and resilient systems. So this is our agenda. We'll start with architecture, the scope of architecture, and formal definition, and then we'll start looking into what are elities, how do they help us, and how do we even identify, where do we get started, in identifying the elities. And then we'll start unpacking into some of the elities. We'll deep dive, learn more about them, as well as do check how do we evaluate and take some trade-offs, and how do they help in delivering the business value. Then at the end, we'll also see some design principles that have helped us during a lot of cloud migration projects. And if we get bonus time, we'll also look into cloud deployment strategies. So the structure of this presentation has been formatted for beginner architects, as well as developers or any other product roles or business stakeholders who are interested in learning about architecture. So what is software architecture? Right? There are various forms of architecture that are available. People say I'm an enterprise architect, solution architect, application architect, integration architect, system architect. Oh my God, there are a lot of varieties of architecture. So, it's really hard to, pinpoint to a certain definition of architecture, because it has been traditionally evolved in last 2 decades in many ways. However, if you see, the core of architecture starts with requirements, which is the basic motivation for building any system, right? So it's very important for architect to actually collaborate with the business stakeholders from the initial phases. That's when the requirements would be discussed. However, requirements are not just sufficient to build the system in a reliable manner. There is more to it. So the aspects, the non-functional aspects like scalability, reliability, maintainability, auditability, security, there are various non-functional aspects that are combined with requirements to form this entire scope of architecture. So in simple terms, architecture is really needed to build the system easily, develop easily, deploy and maintain them very easily, right? So the ultimate goal is to reduce the lifetime cost of the system and improve the productivity of developers and ops teams. Thereby, we are expecting to improve the customer satisfaction, and then business stakeholders would feel that delivery value. So what are elities? So these are, just like mentioned, there are various software qualities or architectural characteristics that we can say, and some of them we also call as non-functional requirements. These are in place to make sure we are building the system desirable for users and stakeholders. So the screenshot here is the list of ilities that's available from Wikipedia. It's a sampling taken from there. And don't worry, we're not going to discuss all these ilities today. Definitely not. But we will definitely deep dive into some of them. Right, so let's see if we can crack one of the formal definitions. So this is from Rational Unified Process and based off IEEE, adapted by IEEE. What does it say? So architecture is the highest level concept of a system in its environment. The architecture of a software system at any given point of time is its organization or structure of significant components interacting through interfaces. Those components being composed of successively smaller components and interfaces. Let's take a pause. So what is it even saying? It's talking about the structural aspects of the architecture. So when we see the core or the main piece starts with piece of code, right? So we group these piece of code files into libraries and then modules or components which logically deliver the functional value. And how do they interact? They interact with various interfaces. It could be via APIs, or if it is a batch component, it could be via the files, or it could be even event-driven. So it could be via the event models. So there are various interfaces between these components, how they can communicate. And this forms the skeleton or the foundation of the system architecture. And this is not it. It is also encompassed with architecture decisions as well as design principles. And these architects generally consider these architecture decisions based on various factors like organizational structure, and then strategy, enterprise architecture, and there are various other external factors that would influence the architecture. That's why it's said as at any given point of time. And this architecture can be pragmatic in nature, depending on the factors. How do we identify ilities? Like I said, it would start from business requirements. So together, we will be seeing some examples, and we'll derive ilities from requirements. It's going to be a fun exercise. The first example, the system must support 10 million users within 5 years and ability to trace user actions. Any guesses? What kind of ilities are we expecting here? Scalability? Availability? Wonderful. Exactly. And auditability. So, we want to scale to 10 million users within 5 years. At the same time, we have to audit the actions of the users. So that's where the scalability and auditability comes into the picture. Next example. The payment systems must be accessible 99.99% of the time. Availability. Any more guesses? The another aspect of it is disaster recovery, because we are making sure we are redundantly deploying the systems and they are highly available. Next one, only authorized users can access sensitive financial data. Straightforward answer. Any guesses? It's security. Next one, new enhancements should be delivered quickly with minimal effort. This is the most repeating requirement everywhere, isn't it? How do we deliver very quickly with minimal effort? Good guesses. No guesses are wrong. So we're looking for something like agility, modularity, because they can be independently developed by different teams, and there are no cross-team boundary delays, so you can deliver them quickly. Last two examples. Users should receive search results within 2 seconds and automatically recover from failures. fault tolerance, resiliency, absolutely, and performance. Those are the ilities we are looking for. The last one, the system must integrate with third-party payment gateways. Bit tricky one. What's that? Adaptability, perfect, yeah, and interoperability, which is equivalent to closer to the adaptability, and then standardization, because when you are working on a payment gateways, you want to adhere to ISO 8583 or some standards, so that if you switch, all your credit card processings would not change, right? So you have to adhere to standardization. Good, we have now seen how to identify ilities from requirements. Why do we even care for them? It is very important because there are certain architecture patterns which would promote certain ilities. So when we know the requirements and when we know the ilities, that's when we start to lean towards certain architecture patterns. For example, if a requirement is to get maintainability, scalability, and security, we could probably go for a layered architecture, a very traditional one where we have presentation, business, and persistent layers. They are independent, they are isolated, they can be maintained, scaled independently. And then when the handover happens between the layers, obviously the authentication and authorization would happen, the security is taken care, right? Another example, say if we want scalability, resilience, and interoperability. We could probably lean towards a microservices architecture where you have these independent microservices which can be scaled independently and then developed independently, and they have limited blast radius. So if one service goes down, it would not impact other one. So we are having that implicit resilience built in. And interoperability, because they can be developed with different technologies and they can interact with APIs as interfaces, and they are interoperable. Another example, cost efficiency, scalability, availability, and no maintenance, or probably low maintenance. And I believe that immediately rings a bell, that serverless architecture, because we don't want to provision servers and not maintain them. And at the same time, we are paying only to what we use. So we are actually bringing in cost efficiency as well. And they are scalable and highly available. Most of the cloud vendors today, they provide us this. Last example here, slightly different to the previous one, scalability with asynchronous in nature, resilience with loosely coupling in nature, and then interoperability. When we hear the word asynchronous, we most likely tend towards event-driven architecture, because we want this event broker to actually hold all those events from the producers on one side, and then consumers consume it from on the other side, right? So these are really asynchronous in nature and also resilient in nature, because if one of the producers or consumers goes down, it is, again, limited blast radius. They are not impacting other ones. And consumers can actually, start from where they left off before dying, right? And interoperability, because producers, consumers, they can be developed with any technology, and then they can just interact with that single contract of event model. So let's get into the deep dive of some of these ilities. We will look into these items today. We'll start with high availability and reliability. So these two terms are often confused to be same. They are related, but they're also different. So high availability is saying that the system needs to be always accessible and available for users. And on the other hand, reliability is saying that my system needs to be correct and consistent. The two C's there. Right? So in this high availability, the key features that we would focus is, we deploy redundantly in different availability zones and regions, and make sure the traffic is routed via the load balancer so that it can smartly route only to the healthy systems. So users would always access the systems, so it's highly available. The focus is always on the uptime percentage. We will very soon see what those uptime percentages would look like. On the other hand, for reliability, we're focusing on accuracy, the correctness of the functionality, and consistent performance as well over the time. And how are we handling the errors? Are they graceful? How are systems using, how are our users seeing these errors? Can they actually come back and work from there if there are errors? And the main focus would be mean time between the failures. How often are we seeing the failures? We'll dive more into the high availability and reliability metrics very soon. So this is a bar graph showing high availability measurements. How do we measure them? You might be already, we often hear 5 nines of high availability, 4 nines, 3 nines. What does that really mean? So generally we calculate high availability by uptime divided by total time. So it's like total uptime plus downtime. What does it mean? If a system is supposed to be adhering to 5 nines of high availability, the maximum possible downtime allowed for that system is only 5.26 minutes per year. This is a standard. We are seeing that as a very business critical system, something like banking, financial, trading, or healthcare, where we cannot tolerate any downtimes. Similarly, for 4 nines, it's 52.6 minutes, and then 3 nines, it's 8.76 hours, and 2 nines is 3.65 days per year. This is a very popular pattern for high availability from AWS blog. What we are saying here is we deploy to 2 different regions, and regions in AWS is basically geographically separated locations. And in each location, for example, US East 1 is one region, US West 2 is another region. And each location would have, again, geographically separated data centers which are co-located. And we deploy our systems redundantly into different availability zones as well as into different regions. And we would continuously synchronize the data across the AZs as well as across the regions. This will ensure that if we go down on one side or one of the availability zones, we always have redundant systems available on other AZs and regions, which would ensure high availability. And reliability metrics. Just before this, on a very lighter note, I was recently asking ChatGPT, how do I explain my 13-year-old about high availability? It said, well, if your pizza is delivered on time, that's a highly available pizza service. And if you have your pizza with all the toppings that you have ordered, it's correct and accurate, so that's reliability. That was a really funny analogy, and I liked it, actually. A good way to explain it to kids, isn't it? Right, so reliability metrics. We often hear this 3 terms, MTTD, MTTR, and MTBF. So MTTD is basically mean time to detect. When your system is running normally and say you have a failure, what is the time taken for us to detect the problem from the time it has occurred to the time we have detected? It's a mean time to detection. And once we have detected, what's the time taken to restore the service? That's mean time to recovery. And mean time between failures is what's the time between each of these failures. So in overall, our objective needs to be to reduce the numbers for these metrics. So the lesser the numbers on mean time to detect and recovery and failures, the more reliable our system is. The last piece in the reliability here is we need to talk about the disaster recovery strategies as well. So disaster recovery is when you have geographical calamities. It is possible that one of the regions can go down. So we want to make sure that the other region is available. In this case, probably US East 1 is down, or we want to just make up our servers live on US West 2. How do we do that? There are 4 different strategies. First one, backup and restore. So when one side is down, what we are saying is we take a backup, restore them all on the other side. But it would involve some downtime, right? Probably in hours. So you are seeing 2 words here, RPO and RTO, which is recovery point objective and recovery time objective. So it's the maximum time that is needed for you to recover from the time of failure is the recovery time objective. And recovery point objective is the maximum possible data loss that you would incur, and that can be bearable. So how long in the back you can go to the point of time where you can restore the data from. So in the second strategy here, pilot light, what we are saying is my data is live on the second side, but my services aren't running. And our system is active on one side. So if there is a downtime, I would just scale up all my services on the other side and route the traffic to the other side, which is better than backup and restore. However, it still incurs some RPO and RTO, which is probably tens of minutes. Next one is warm standby. So what we are saying here is our data is live on the other side. We are also running some critical applications in a very minimal stack. And if there is a downtime on the main side, I would just scale up these instances. So it's much more faster and better than the previous one. Again, we can still incur a few minutes of RPO and RTO in this case. All these three strategies are called active-passive strategies because we are always active on one side and passive on the other side. The last one here is multi-site or active-active strategy, which means we are live on both the sides, receiving traffic always on both the sides. And if one side is down, my other side is always taking in the traffic continuously. There's no impact, no downtime. So we are saying near zero downtime, near zero data loss in this strategy. You can see from blue to red, the cost is also increasing. That's because we are building highly redundant systems with data replication and storage services across. So if our system is business critical, it is more likely to fall onto the right side of the spectrum. And if it is like lower environments and non-business critical application, it can come onto the left side of the spectrum. So it's up to us to decide where do we want to take trade-off, cost versus availability, right? Next one is chaos testing. So chaos testing is also a very key aspect for a very critical application. This is the way we find the system weaknesses. So what we are doing here is we're injecting a fault, a service disruption into the system to test our monitoring and alerting capabilities and our recovery procedures. So how do we know that my mean time to detect and mean time to recover are actually less in production? How do we guarantee that? It is by actually, doing these game days. We call them as game days where there would be a chaos monkey who would really go and anonymously inject a failure. None of this would be known to any of our team members. So we would really test how quick we get those incidents, how quick our teams are getting paged, and how quickly we can actually identify the root cause. Are our logs providing all the required information? And then once we identify the root cause, how quickly are we able to fix it? Do we have all the required automation in place to be able to do a single-click deployment and release things in a faster pace? So it can really uncover any hidden issues, improves our architecture, as well as validates the recovery procedures. Next one we will go into is scalability and elasticity. Again, confusing terms, right? These are once again related ones. They give and take from each other, but they're also a bit different. So scalability is ability to handle the increased load. We are planning for future growth, and our system is designed for parallel processing, so we can always scale them manually and then make our system ready for future volumes. But there's still a manual intervention required. And on the other hand, elasticity, it has the ability to adapt dynamically to increased volumes. So the word dynamic is very key here. So what we are saying is we can actually automatically scale up and scale down as the volume fluctuates. It can dynamically adapt to the volume fluctuations. So these are resource provisioning strategies. Like if we see just the scalability alone, or an on-premises servers where we had to provision all the servers upfront, because procuring servers on on-premises is always like time-taking, right? So we make sure we just throw a lot of servers. We waste a lot of resources just for those 2 days, like Black Friday or Christmas Day, right? That is over-provisioning. And we are not left with most of the choices in on-premises. And scalability is where you go into that certain period of time and add few servers. However, it is not guaranteed that the 2 additional servers you have added would be sufficient, more than sufficient, or insufficient. It could still lead to under-provisioning or over-provisioning without elasticity. But when we have both elasticity and scalability, you can see these 2 lines, blue and green, go hand in hand, which is like you're not under provisioning, you're also not over provisioning, but you are scaling up and down as the volume fluctuate. So this is where most of the modern systems would require and would wish for. Performance. There are various types of performance testing that we do to ensure that our system is future-proofed and to ensure that our system is reliable and performing as per the SLAs. So load testing is when we pick up our 1x volume, generally a standard regular day volume. If it is a batch processing, say I can process my system with 35 million volume, or if it is APIs, say I can generally process 1000 TPS, for example, right? So we load test our system to ensure that it is working healthy with that load. Stress testing is, well, I know my system works for 1x volume, but what happens if I throw 2x onto it? All of a sudden I increase my volume to 60 million. Does it still behave correctly? Or where are my system limits? So stress testing is really to understand your system limits. Scalability testing, this is to increase the growth gradually and test if our systems are actually scaling as the volume increases. The last one, endurance testing here. So it's like for long-term reliability, right? So if you are producing sustained load across the period of time, is our system behaving well in that sustained load? So that's the endurance testing. There are various key performance metrics that we measure our system with. Mostly on the infrastructure side, CPU and memory utilization is very common. And then on the application side, it could be TPS, response time, throughput, latencies, file size impact, error percentage. Likewise, many other application-specific performance metrics can come into picture. 3 key terms that we talk when we talk about system performance: SLA, SLO, and SLI. So SLA is service level agreement. That is a legal contract that we are making with our customers. So it could be an example of my system serves 1000 TPS, or my batch processing finishes within 1 hour. That is where we are legally binded to adhere to those SLAs. And SLO is, we're saying, okay, let's be ambitious and have some internal goals. If we are committing to 1 hour to the customers, can we finish that within 45 minutes? So these are our internal targets to be able to achieve SLAs. And if we have an end-to-end system with 1 SLA, we could probably end up having multiple SLOs for each component, because a system can be composed of multiple components. So it's important to understand the combination of SLOs are actually resulting into that single SLA. SLI are the key performance metrics that we just talked, like response time and TPS. These are the service level indicators with which we measure the performance. A very sample graph that any system should have as an architect is, what are my SLIs, the service level indicators, for 1x volume, a 2x volume, and this is my breakpoint. If we do not know the breakpoints, look forward for the surprises from production. So we want to future-proof our system, understand our system better before the actual volume comes in, kicks off. Cost. How many of you have heard the term frugal architect? Not bad. So the term frugal has been introduced by AWS recently. So why do we even need to care about cost? Traditionally on on-premises, it's all about capital expenditure, which means, we procure servers once in 5 years, and then they are, not taken care or worried about until it is hardware refresh due, right? And we don't throw any money again. But the game in the world of cloud is entirely different. Because you are receiving monthly bills, now it is not any more capital expenditure, but it is all about operational expenditures. We would see surprising bills if we don't really, design for cost efficiency in cloud. So some of the, tips or principles that would help is they are both proactive and reactive in nature. So proactive is where we plan upfront and we design upfront to make sure our resources are consumed and right fit, and we are not wasting resources. Some of the examples could be like we could use reserved instances, savings plans. Most of the cloud vendors, they do offer discounted rates. Spot instances. So when we know that our system is fault tolerant, we could go for spot instances because there is no reliability on them, right? Like you could lose spot instances at any point of time. So probably we could use them in non-prod environments, but you get for at least 80 to 90% of discounted rate. So why not save some costs there? Reserved instances, generally they gave it for 3-year plan. It's probably like more than 50% of discounted rate. When we know that our system is going to run for next 3 years, can we actually go for that? There are flexible plans as well, like you don't have to stick to certain EC2 instance type. There is flexibility to change EC2 instance type, but also get the reserved instance discount rate. So other things like we can use auto scaling, and we don't have to really over provision. Compute optimizer, where it would give us some references of where we are actually wasting resources and how can we upgrade resources to something like Graviton. Because if you know Graviton instances, generally they are the same general type instances, but they're available, they perform well, but are available for lesser cost. So these are kind of examples of proactive way of saving costs. We can also design for serverless. For example, if we are not receiving load 24/7, why do we have to spin up our EC2 instances all the time, right? We can go for serverless architecture and just pay for what we just use. On the observability side, because it's very important to observe our system. Without observability, we cannot understand where are we actually wasting or getting these huge bills. So it's important we set up budget alerts, we set up the cloud watch, understand where our resource wastage is going into. Then another important one, which was also very helpful, turbonomics. Anybody heard about turbonomics? Yeah, so it's a vendor tool. It is very helpful. It is able to identify every single wastage that we are incurring in the cloud. It could be idle EC2 instances. It could be unused EBS snapshots or DB snapshots. It could be your S3 storage, which has not been frequently being used. So it just gives us all the hints on how can we actually improvise in those situations. And it's not just that. If we authorize, it can even terminate those idle instances. Cautious, we do that on non-prod, not in production. Don't create unnecessary noise in production. But certainly very helpful. It does a job in saving costs. We are coming to the end of this session. We'll go through some design principles that help us attain these ilities. first one, technology-independent interfaces. I cannot emphasize enough how important it is. If we are in the world of multi-cloud, and how do we make sure we are cloud agnostic? And how can we easily port our code from one cloud to another cloud? Or how do we port our code from on-premises to cloud, really incurring very big changes or code refactoring? This is a very key principle. So how do we achieve that? We have to create the interfaces which are technology independent. So all our customers or the callers of our classes are really calling our interfaces, which would not give them any hint if we are actually calling a method to AWS or GCP or Azure. So let's abstract that via interfaces and make sure that we are building consistent code. So when we move this code to cloud, we are really not impacted. Or if we move this code to a different cloud vendor, we are not impacted. So it gives those benefits of when reduced vendor lock-in, consistency, cost optimization, because we are not really rebuilding everything again when we are changing the cloud vendor. It is not always possible to build it in that way, but there are definitely some common classes we can build it in that way. If we go to AWS native instances like Lambda or DynamoDB, probably there is limited scope to build those, but there are most of the cases where we can build them. So this is one of the examples I wanted to showcase. So in here, we are seeing a storage service, which is just doing the basic operations of write, read, and delete. And the caller of the storage service is really not worrying how those writes and reads are happening. It is up to the implementation class. It could be an HDFS storage service on on-premises, or it could be an S3 storage services on cloud, right? Or even it could be a local file system storage service. Our developers would want to test this application on local laptops. Right? So at runtime, we are actually injecting the implementation without really impacting our customers. So it also brings in those solid principles. Anybody aware of solid principles? Most of us, right? So it brings in that interface segregation and single responsibility. So why do we want to really add anything related to S3 keys on HDFS storage, right? We want to segregate, let the classes hold that single responsibility. And if we are changing that class, it is only for one and only one reason. So that's the first design principle. Next one. So this is multi-module application architecture. This also was very helpful for us during cloud migration. What we are saying is, okay, we have this on-premises code, and it's a really big piece of set of components. How do we migrate this to cloud, really without impacting any key releases to the on-premises, and also not duplicating the code for cloud? So what we could do is abstract everything which is core application module into core module, a Gradle module. And then make it highly configurable. Anything related to on-prem configuration, for example, your vault keys or your any API details or anything related to Ansible, your deployment, all the on-prem configuration, pack it into on-prem config module. And then everything related to the cloud, for example, your S3 keys and then PEM keys, for example, or any other runtime variables related to the cloud, they can all go into cloud config module. So these are different Gradle modules. When we build for on-premises, we only build core as well as on-prem. We don't have to worry about cloud, right? What is the advantage? So say for cloud, if you're using AWS, obviously we will be using AWS SDK. How do we interact with S3 or any of the AWS services? What if AWS has got suddenly, one of the libraries has got some vulnerability, and then we have to do a break fix in production on-premises? Are we not stuck if everything is in one single code base? Our cloud is not system of record yet. Why do we want to impact our critical path on-premises if we are merging our cloud into that same code base? So this segregation is actually giving us that benefit and flexibility to segregate both the configurations and segregate both the release cycles. So we can really schedule any number of releases at any point of time on both of these environments independently. And at what cost? We are still having that same core application module. We are not duplicating it. Next one, multi-tenant architecture. So in any enterprise, it is very, very common requirement where you have set of core processing modules which needs to be repeated for multiple tenants. It's the same functionality that is expected for multiple tenants. There are various strategies you could do this. So for example, we can have one GitHub component with different tenant configurations induced at runtime. But the major drawback of that process is if you have a new feature that needs to be released for tenant B, for example, then you have to go and ask, hey, tenant A, are you ready? There's a new feature coming in. Can you please coordinate with us during the release? So we will just end up really coordinating these release cycles across all the tenants if it is single code base. So what we can do to avoid those situations is we extract everything that is core application, which is common to all the tenants, into a framework. It is a library, a separate GitHub repository, and then everything that a tenant would require would be extracted into a tenant per tenant deployable component. They would have a different GitHub repository. But how do they link to the core application? They add the application framework as a dependent library in the tenant module. So it's similar to our open source library usage. So a tenant A, it is using, say, release version 1, and there's a new feature added to the core application framework. We just do a new release version 2, and the tenant B, whenever it is ready, it doesn't have to really coordinate when release 2 is done. They can actually wait and they can go as per their priorities, and whenever they are ready, they can actually upgrade to this version 2. So there is no really required hassle that we have to go through to do this cross-tenant coordination when we do this multi-tenant architecture. So we are still reusing the code. There is no code duplicacy. And then we can actually do isolated release cycles. The other major thing that we would benefit is limited blast radius. So you're keeping these tenants into cells. If anybody has heard about cell-based architecture, it overlaps with this term. So you're keeping these tenants into cells, and then the blast radius of any impact of this tenant is only pertained to that tenant. We're not impacting other tenants. All right, that's the end of the session. We do have 6 minutes. If everyone is still interested, I can very quickly go through the cloud deployment strategies. Oh, good, or still hungry? All right. So I've saved these as appendix slides just in case if you overrun, I could just hold off there. So these are very popular cloud deployment strategies. We'll go through them quickly. Blue-green. So you might have heard about this term. So what we are saying, we'll have parallel environments, blue and green. Blue is our system of record where it's receiving the production traffic. And the green is passive side, where you can test your new releases. And once you gain the confidence, you can flip the traffic to the green environment. So low risk, and very easily, without impacting the customers, you can move to the green environment, and easy to roll back as well. And the next strategy, canary deployment. Anybody heard canary? So it's a gradual way of increasing the volume and introduce your new feature with slow volumes, so that your phased customers or proportionated customers would only be impacted with your new features if at all it has some problem. So you're really testing your new features with increased level of volumes gradually. And A/B testing, it's really needed for version comparison if you want to compare apple to orange with some new changes into your software. How do they both behave in terms of non-functional aspects as well as functional aspects? Verify the user experience from A to B. Verify the performance from A to B. So that's how we do A/B testing. Next one, rolling update. If we are all familiar with containers, we know this very well. So if we have like 1,000 containers, how can we actually just do the rolling upgrade without bringing down all the containers at a time? So what we are saying is we just upgrade one container at a time. So the user traffic is still live on the other healthy containers. And it's easy even if you want to roll back as well. So parallel production or shadow deployment. This is a very, very key important strategy, I would say, if you have really big application which is moving to cloud. And how do you make sure you're confident enough and you're not risking anything in production that would go bad? Is we build a parallel environment of our on-premises, on cloud, and make sure our user requests are coming on both the sides. So both on-premises and cloud are doing same functionality. But our system of record is still on-premises. We'll send the result out from the on-premises. But we get a chance to compare our cloud against on-premises. Are we matching the result? So in case of a lift and shift models, generally, the application is same, but we expect the functionality equivalence. So we want to make sure the output of on-prem is equal to the output of the cloud. So parallel, production parallel is a very, very important one that helps us to understand that our system hasn't been changed after we move to the cloud, and there is no risk to flip the traffic. So one fine day, probably run it for 2 or 3 months in production parallel, and one fine day when we have gained that confidence, on the go live day, just flip the traffic. So it's easy. But there's a cost associated to it because now you're running both the environments for a few months. Next one, recreate the deployment. It's purely completely rebuild. It's not recommended. And a legacy model too. We have seen this from ancient times where you replace the entire system with another system. So you're incurring a very big downtime to the customers. Next one, phased rollout. So we are choosing MVP of users in the first phase, and then few set of users, targeted classified users in the second phase, and then slowly, gradually rolling out to different types of customers in third phase. So it's easy for us to understand that within each phase how system is behaving, and then we limit the blast radius to that phase. So it could be set of users or it could be set of functionalities. So we can do an MVP release with certain functionalities to start with, and then slowly increase the set of features in different phases. So once again, it helps us controlled rollout of changes, and it helps us control the impacts in production to limited audience. So feature toggling, I'm sure all of us are definitely aware of this term. How do we make sure that the new feature that we have introduced in production is not buggy, or if it is buggy, how do we stop rolling back everything into previous version, right? Simple solution, have a feature toggle. There are a lot of vendors available to provide this feature toggling, like inbuilt out of the box, we can just plug them in. So anytime you release a new feature, there's a feature toggle, which can be switched on or switched off without really rolling back the entire production release version. Next one is immutable deployment. This is mainly useful if you have in place, if you have infrastructure replacement that you have to do, probably RHEL 6 to RHEL 7 or another major version, where you cannot do in-place replacements or in-place modifications. So we recreate an entire system of the same thing as a different redundant system, and then we test that system. If everything is fine, change the traffic to that system, and then switch off this old system. Right, so I think these are the different cloud deployment strategies I wanted to share. We are right on time. And yeah, Please feel free to connect. This is my LinkedIn. And thank you so much.